Hi, welcome to the video on logic behind decision tree. By the end of this video, the learner will be able to explain entropy and information gain for splitting a node. In the previous video, we understood how Gini impurity helps in selecting the best input variable for splitting in a decision tree classifier. In this video, we will look at another criterion known as information gain. Let's start with the simplest of the analogies. Consider these three nodes. Can you guess which of these nodes will require more information to describe them? Remember here, plus sign represents students who play cricket and minus sign represents students who do not play cricket. Now as you can see here that node 3 is a pure node since it only contains a single class, whereas node 2 is less pure and node 1 is the most impure node out of these three nodes since it has a mixture of classes and the percentage distribution is 50% in node 1. So as the impurity of the node increases, we would require more information to describe them. For example, for node 3, we could say that everyone plays cricket, so less information is required to describe the node. While for node 2, we would need more information to describe who plays cricket and who does not. And hence node 1 will require the most information compared to node 2 and the node 3. And hence we can say that the more impure a node is, the more information is required to describe it. Let's consider an example to better understand this. If you look at this split at the right hand side here, it is leading to a less homogeneous node as compared to the split at the left, which is producing completely homogeneous nodes, and we can infer that split on the right is giving less information gain. Information gain is nothing but the difference between information needed to describe the parent node and the information needed to describe the children node. As children node get more homogeneous, the information required to describe them is less and hence the information gain is more. So, we can say that higher information gain leads to a more homogeneous or pure node. Mathematically, this information gain is calculated as 1 minus entropy. So, let's look at how we can calculate entropy. We can calculate the entropy as minus P1 log P1 minus P2 log P2 minus P3 log P3 up to minus Pn log Pn, considering there are n classes. Here, P1, P2, P3 are the percentage of each class in the node and the base for the log would be n. To understand how entropy is calculated, let's consider this node. Here, the percentage of students who play cricket is 0.5 and the percentage of students who do not play cricket is also 0.5. As log of 0.5 is minus 1, the entropy for this node will be 1. Let's consider one more node. You can see it as a pure node as it only contains a single class. Percentage of students who play cricket in this case is 0 and those who do not play is 1. So after applying the formula on these numbers, we will get entropy as 0. So if we compare the entropy values here, we can say that lower entropy means more pure nodes and thus more information gain, while higher entropy means less pure nodes and thus less information gain. So if we compare the entropy values here, we can say that lower entropy means more pure nodes and thus more information gain, while higher entropy means less pure nodes and thus less information gain. Similar to Gini impurity, it also works only with categorical target variables. Let's now look at the steps to calculate the entropy for a split. We will first calculate the entropy of the parent node, and then we will calculate the entropy of each child node. Finally, we will calculate the weighted average entropy of the split using the same steps as we saw while calculating the Gini. Weight of a node will be the number of samples in that node divided by the total samples in the parent node. If the weighted entropy of the child node is greater than the parent node, we will not consider that split as it is returning a more impure node compared to the parent node. Let's use these two splits and calculate the entropy for both of the splits. Let's start with the split on performance in class. This is the split that we got based on the performance in class. The first step is to calculate the entropy for the parent node. The probability of play and do not play cricket is 0.5 each, as 50% of total students play cricket. So the entropy for the parent node will be 1. Similarly, for the sub-node above average, the probability of playing is 0.57 and the probability of not playing is 0.43, and hence the entropy will be around 0.98. For sub-node below average, the probability of playing is 0.33 and the probability of not playing is 0.67, and hence entropy is 0.91. Finally, the weighted entropy for the split on performance in class will be the sum of weight of that node multiplied by the entropy of that node. For performance in class, entropy will be around 0.959. Here, you can see that it is lower than the entropy of the parent node, and hence it is returning more pure nodes compared to the parent node. Similarly, we will calculate the entropy for the split on class using similar steps. The weighted entropy for the split on class is 0.722. Here, we have calculated all the values and we strongly recommend you to calculate them on your own and then compare the results with the values as shown here. Now we will compare the entropies of two splits, which are 0.959 for split on performance in class and 0.722 for split on class. As you know, information gain is calculated as 1 minus entropy, and these are the values as shown here. For performance in class, information gain is 0.041 and for class it is 0.278. Remember, we have discussed lesser entropy or higher information gain leads to more homogeneity or the purity of the node. And hence, based on the comparison, split on class will produce more pure nodes. This is how we can make use of entropy or information gain to decide the best split. So we have completed two methods for finding the best independent variable for a decision tree classifier. In the next video, we will discuss the decision tree regressor.